Hello and warm welcome to you, and thank you very much for joining this session. I am Amir Attarha, Veluche Power Product Manager in Siemens. I, along with my colleagues Pankaj, Chauhan, Diwakar Agrawal, Satish Agrawal, and Gaurav Saharawat, work closely on this topic, which I present today. Identifying unique power scenarios with data mining techniques at full SoC level with real workloads. Let's get started. We will look at the power trends. Then we look at the Veloce Power Solution overview, which enable us to generate power data. This power data needs to be analyzed, which is the main topic of this paper. And we will approach by traditional methods and data mining methods. At the end, we present some of the experiment results of this paper, and with summary, we'll wrap it up. Let's look at power trends. No longer we have VDD scaling with technology shrinkage. Hence, the power has become one of the key challenges for entire semiconductor industry, irrelevant of the product family. We commonly hear failure of high-profile chips in the industry. Last summer, there was an article about NVIDIA RTX 3090, which indicated major struggle with power issues. When users tried launching New World game from Amazon on RTX 3090, it will sometimes cause it to completely fry, forcing those impacted to contact manufacturer for refund. This is not the only case. There was another article on Intel Ice Lake. It mentioned Intel Ice Lake SP is unusually power hungry for a chip made with 10 nanometer. It is consuming more power for doing the same computation compared to previous Cascade Lake on some benchmark. It is very important to do power analysis and estimation with end user software application. This example of RTX 3090 power-related issue might have been caught if they had run the example pre-silicon, the Amazon game, the New World. Still, many companies are focusing only on performance, and they see power as an afterthought. Power analysis need to be integral part of the design methodology to ensure successful products. At some companies, some companies are realizing this, and they are doing early power analysis, but they're facing new challenges. With generation of power data for each IP over each RTA revision, analysis becomes extremely time consuming. It requires quite a lot of expert time. This is the problem that we are specifically trying to address in this session. Let me go over first Veloce Power Solution overall slide. So Veloce Power Solution, by generating many power profile and heat maps, enables users to perform deep power analysis of their design with various end user software applications. With Veloce full visibility, power profile and power metrics can be generated for entire design. In addition, the power tracking capability enables to track this information in lifetime of the project for each RTA revision and see the trend of their progress in terms of power. For power estimation, not only we can generate traditional FSDB and SAFE files that are used by power tools, we also have tight integration with power tools to stream data directly to them to ensure much faster time to power numbers and less disk space, as we don't have to generate these massive FSDB files. We also enable power aware verification at SoC level with UPF for ensuring functionality of the design with sophisticated power gating for system level test. Firmware validation and software tuning can be accomplished with Veloce power-aware verification technology. We have invested a lot in shift left with regard to power. By shift left, meaning to be able to do more regarding power earlier in the design cycle. Being able to accurately predict power, predicts earlier, and then have enough time to take the right set of actions and know the outcome of this action all before tape out. It starts with generating the power data. How fast can it be generated, and how good and accurate is the data being generated? Veloce Power solution generates power analysis data with cycle granularity for huge benchmarks like Manhattan, Car Chase, Angry Bears, and Aztec in just few hours. Next step is analyzing this data. This is where our power profile plot and key metrics come into picture. Key metrics like clock gating efficiency and flip-flop efficiency, power profile for IPs, and hotspot contribution for different blocks in the design is now available from Veloce directly without the need to go to any power tool. This is allowing power team and designer to identify and then focus on the right IP for the right period in the workload. So we identify the IP and the period in the workload that is relevant much sooner in the project lifecycle and figure out next step and right next actions. Next comes experimenting with proposed changes for power reduction. Users want to be able to have a fast turnaround time with RTL updates to understand if such changes are reducing really power consumption or not. By allowing recompile and running on just a small IP component with the SoC stimulus, this has allowed the customer to be able to validate the result of RTL changes within hours, as compared to 3 to 4 weeks that it used to take earlier. And it has been a real game changer for them. Across the timeline of multiple SoC and subsystems, there will be many RTL releases, and user and designer would like to track how the changes are affecting power across the project. The Veloce Key Power Indicators dashboard help users to do this to ensure that they do not miss any outliers, deviation, with any RTL update, and deliver this solution with confidence. Frequently, we hear from some of the customers that of all the workloads, we even don't know which workload is exercising interesting scenarios for power. With fast generation of power profile, we can address that question. So the design and power team have a high-level view of the workload in terms of the power behavior. Note that this data is being generated for each IP. Consider for each RTL release, this data is generated for each IP. Now, analysis needs to be done, but it's going to be very labor intensive. This is what we are targeting, automating some part of this data analysis. For power analysis, we are taking two approaches: the traditional KPI tracking and data mining. In the KPI tracking, we capture data and record key information in a centralized database. This data is tracked over the lifetime of the project. Trends are explored, and comparison of IP's behavior in regard to power for each test is highlighted. In the data mining method, we initially define a higher level of abstraction concept as power behavior state, or PBS for short. We're going to talk about this one later. Then We extract key data from power profile in terms of PBS. We cluster the data based on PBS and reduce the scope of analysis without losing key information. Then we identify tests which exercise different PBS scenarios. These two approaches are will be discussed in detail here. Long time ago, we moved to metric-driven verification with functional verification and functional coverage. We are now providing the same metric-based analysis for power analysis. We are collecting power information and place it in a centralized database. So for each RTL revision, this data is collected and maintained in the main database. This allows visualizing power trends and comparative analysis of power data for various IPs. So rather than holding the massive power data, you can get your key power information recorded in your main database and then use that one for your trend analysis. This is a dashboard that we provide that allows you to have your power database for different RT releases, different tests, and you can compare the trend for your key power indicator. You can look at your clock gating efficiency. You can compare it with the reference database that you have and see whether you're doing better or worse. Your structural information is available. Also, your power domains, if you're using UPF, it is available, and the coverage on your power domains, how well you are exercising different power domains. Various metrics are tracked over RTL releases and over various tests. And this is really important that you can run it for different tests and different RTL releases. And the data are, the total power, peak power, the component-based power. What is your combinational power or logic power? What is your clock power? So you will have that information. And you can use that one for your trend analysis, and that's a key point. Regarding comparative analysis, for instance, I have run for an instance shader of a GPU two tests. One is Angry Bird and one is Manhattan. So I can see how each of these tests are affecting my IP and kind of do comparative analysis. I can do comparative analysis based on tests or different RTL release that I have. Also now, if I want to now dig deeper in Manhattan, then I can expand that one and see over time how my Manhattan is run in this shader that I'm interested to look into. So this is another view of the power trend analysis over RTL releases and tests, and there are various metrics that you can compare. And here we do some of the statistic analysis to get you to direct, to focus your attention to the areas that they are important, rather than looking at all the data. So for instance, here it shows instances which consume 5% power compared to reference data and database. So if you increase the power consumption, you can focus on those instances specifically to see what happened. Now let's introduce the power behavior state. Now we are shifting to the data mining part. So power behavior state is defined based on our observation of most of the power profile that you analyze. As you can see, you can come across four types of power behavior. Calm, and this is referred to when your IP is in the idle state, so there's not that much activity going on, and you see a steady state of low power consumption. When the application gets started, you suddenly see a surge in the power, a lot of activity, and it seems like a tsunami. That's what we call it, a tsunami. There are similar scenarios. They are sudden surge and sudden drop, and we call those choppy. And there are some scenarios that the high activity happens, and then there is a for sustained amount of time the activity stays, and we call it active. In this power profile, this categorization is shown. So initially we have a calm stage, then suddenly we see a tsunami happening. Then we have an active state for a while, and another tsunami followed by a calm state. And you see a choppy here, followed by active state. And that's basically the basic definition of power behavior state. Is not is a fuzzy definition, but it's very relevant for this data mining behavior that we are looking for. For data mining, we follow the method of collecting the data, really power data collection. So we do this one with Veloce Power solution. Then we do the data wrangling or data cleaning to clean the data. Then we analyze the data and we did the feature extraction. And this is really the key step that we followed. We have to concentrate, and the features are extracted based on the knowledge of the, our expertise in power, and the analyzing the various power profile and other metrics that we look into it. And these are the features determine the quality of clustering that we do. And by clustering, it's really we categorize the different power behaviors in our PBS state. We do further analysis, and then we do another clustering, and we can extract information out of it. So in this picture, you see that data, power data is collected for various RTL releases, various tests, and various IPs. In layer 1, after the feature extraction, we do clustering of the IPs. And in layer 2, we do the PBS distribution. And PBS for power behavior state distribution that I will show you the experimental result. Okay, this is the first layer of clustering. As you can see, there are 3 different IPs from design 1 that our clustering algorithm has put it in one category. As you can see, they have very similar power behavior. So if as a user, as a human user, also if you look at it, you would consider them to be of the same behavior, while they are for different IPs. Here, there are 3 different IPs from design 1 that they are placed in different categories. And visually also I would put them in a different categories because the way they behave is different. And this is our first layer of clustering that we do. And this is the experimental result table for this. For we had 3 big designs. These are big SoCs, and we have the IPs. These IPs are not small IPs; they're big IPs. Original IPs are 81, 49, 26. After data wrangling, we got some number of them deleted, and then we are really clustering it to 4 categories. And here are the number of IPs, as you can see, distributed in different clusters. And what this one is going to tell me is, okay, so if as a power expert, if I want to look at this design, rather than looking at all the IPs, I can look at one IP, one candidate of each cluster at a time and see how does it look like. And the others are going to be of the same type of nature. So for this one, I can pick one of them and look at this one, also one of them. Rather than looking at 50, I can reduce the scope with a smaller domain. Here we are showing the experimental result for PBS distribution across all the three tests that we run. And these tests are really long workloads. They are millions of cycles. And this, as a power expert, when you review this one, you want to look at it and say, okay, so this cluster one of design one, what is his main uh, profile of his power? So I can see these are mainly calm and there are some active region. And if I pick another one, for instance, this one designed to cluster one. So I have some calm area, I have some choppy, I have quite a lot of tsunami and quite a lot of active region. And if I look at this one, so it has a lot of choppy. So I can now look at this one for different power optimization, different power scenario that I want to work on my IP. I can use different basically cluster and different IPs for that time period. So kind of it gets you from tons of data to focus area to look at those for further analysis. So in summary, Veloce Estrado has the capability of full visibility and has the highest capacity. You can run 10 plus billion gate design easily with the stability of the system. Architecturally designed for really can handle huge design, and you can run your end user software application on it and collect the power behavior of full SoCs. This is a capability that enables you to capture full workload with clock cycle granularity power profile. With this, it comes now you are able to, for every RTA release, you can generate that data. So regression-based power data collection is possible with real workload. And for that, you really need a way of analysis. So what we presented is both traditional data tracking, where enables you to look at each week of your RTL and power behavior and how the trends look like, and a new data mining scheme, which can provide significant value to get to the key items to look at it. The higher level of abstraction that we presented, we hope that enables further automation in analyzing power-related data. So instead of looking at data as a disjoint items, we look at it a little bit higher level and analyze it this way. This concludes my presentation. I really appreciate your time and I would like to thank you for attending this session.